Welcome to the course on power quality. Today we will be discussing the numerical examples on power factor corrected buck boost single phase converters. Starting with the first problem, the design a single phase power factor corrected AC DC non isolated buck boost converter in continuous conduction mode operating at 20 kilohertz with the following specification with input voltage of 220 RMS, frequency of 50 hertz, single phase AC supply, the DC output of 180 volt and power output 900 watt with the output voltage triple less than 2% like. So, well, this is the typical circuit that we have AMI filter, then diode rectifier and followed by the buck boost converter, which is used for controlling the output voltage as well as to providing the sinusoidal and unity power factor current at the supply. And after designing it, developing the model, these are the typical waveform, because typically supply voltage and supply current. You can see the supply current exactly in phase with the supply voltage, and it is close to sinusoidal current. So, that your harmonics also less as well as no reactive power voltage is there, and you are able to get almost unity power factor. And this is the inductor current, which is continuous conduction mode as it is already given in the problem, and this is the of course, the output voltage corresponding to. Well, coming to the numerical solution part, the output voltage VDC of the buck boost converter is given in this relation, VDC equal to D upon 1 minus D V in for this buck boost converter, and the V in, which is the typically the converter input voltage, is calculated from average of the supply RMS voltage which is available after the diode rectifier in the circuit. So, putting the value, we get this as 198 volt, and therefore, the value of duty ratio can be estimated from the relation of given above. So, putting the value in this case, we get the duty cycle 0.476. This is less than 0.5. So, it means the converter is operating in buck mode of operation, and the input current of average input current, which is of course at the output of diode rectifier, can be calculated from power divided by average voltage. So, it comes like from 900 divided by 198. So, it comes 4.55 ampere like. So, considering the 30% current ripple for the designing of the inductor for continuous current conduction. So, that is the value of the inductor current from the relation of the input, that is D V in, that is the voltage applied for on period, and this is the 30% current ripple and with the switching frequency of typically of 20 kilohertz. So, if the value that it comes 3.5 millihenry, and the inductor is selected greater than this above value, which is 4 millihenry, to ensure the continuous conduction mode of operation over a wide operating range of the supply voltage as well as of the load like. So, considering the condition of maximum ripple at the output voltage, the design of capacitor DC link capacitor output capacitor is here, that C D equal to I D C upon 2 omega delta V D C. We already discussed it does not depend on switching frequency, it depends on the load current. It also depends ripple in the output voltage, and of course, on the second harmonic is there, that is on supply. So, keeping the value or substituting the value of all these, so it comes 2.21 millifarad. So, maximum ripple voltage across CD considered as 2%. So, the value of DC link capacitor is selected little higher than that standard value of 2.4 millifarad, and the diode bridge rectifier output is fed to a low pass filter tuned at 1/10 of the switching frequency to suppress the higher order harmonics. So, therefore, an LC filter is designed for this purpose, for which the capacitor is calculated from this relation, where theta is the angle between the your supply voltage and supply current, which is taken here just not to have any reactive power burden, only as a 1 degree, and then putting the value of output power, then the supply RMS voltage, then the typically corresponding to the peak voltage of supply and the your supply frequency, it comes typically order of 1.1 microfarad. So, where Vm and Im are the supply peak voltage and current, and theta is the displacement angle between supply voltage and supply current. So, the capacitor here normally we select a little lower. So, it is selected like 440 nanofarad. While the designing the inductor for this LC high, you can call it the AMI LC filter, the source inductor is taken into consideration. Therefore, an accurate filter design is essential for power factor correction converter, and higher order harmonics induced in the input side by switching frequency of solid state switch is eliminated by using this LC filter. So, filter inductor design is given here from this relation from the RMS voltage divided by power, that is equivalent to, you can call it like a kind of resistance, and then this is the typically the frequency here for the corresponding, and putting the value corresponding to for this inductor, I mean we get this total inductance value 5 you can call it like after the source inductor it comes 5.83, and the cutoff frequency of the filter normally consider 1/10 of the switching frequency. So, filter inductor is calculated typically order of, you can call it 6 millihenry. So, that gives the EMI filter design along with the design of other component of this your buck boost converter with power factor correction in continuous conduction mode. Coming to the second example, the design a single phase power factor corrected AC/DC non isolated buck boost converter in discontinuous current mode of operation, also known through the control of voltage follower approach, and operating at 20 kilohertz, and with the following specification of input of 220 volt 50 hertz single phase supply and DC output of 240 volt, and power rated is 500 watt with the output voltage ripple of less than 2% like. So, this is the typical circuit of this buck boost converter. We have EMI filter, we have a diode rectifier, after which we are putting this buck boost converter, and this is we are designing in DCM. So, it means this inductor is designed in discontinuous mode, and of course, with this we control this by voltage follower approach, only the output voltage is regulated by design since it is in DCM. So, it gives inherent power factor correction at the input supply. So, after designing the component and with those component and with power control, a model is developed, and from which you have a supply voltage and supply current. The supply current is in phase with the supply voltage and almost like a close to sinusoidal, and you can see this inductor current is discontinuous, as this inductor is designed in discontinuous conduction mode, and this is the typically the load current and output voltage. You can see clearly here that is a quite good quality output also here. So, coming to the numerical part of the design from the relation of output voltage of the this buck boost converter. So, output voltage is in terms of average input voltage, and the D upon 1 minus D, that is the relation for buck boost converter, where D is the duty cycle, and this duty cycle if it is below 0.5 then it is the buck operation, and above 0.5 it is a boost operation. So, for this we from the supply, because after diode rectifier we can find out the average voltage in terms of the supply RMS voltage. When we put the value it comes like 198 volt. So, therefore, the value of duty ratio can be calculated from this relation. So, putting the value we get the duty cycle equal to 0.547, and this you can say it is above the 0.5, it means there is a buck boost operation of this converter for the this given condition, and we can find out the input average current, that power output power divided by average input voltage after the diode rectifier. So, putting the value and it comes 2.53 ampere like. Well, the designing of this inductor in DCM. So, for boundary condition the value of the inductor is designed for this here. I mean this is designed for on period. During on period we expect the ripple will be corresponding to twice of the peak of input current. So, that is the reason you have start from 0 and go to twice the peak. So, that is the reason that you have a large ripple permitted in the sense of twice, and then the switching frequency. So, this is the typical relation, but just putting the value of your R in by this, and then in this expression high frequency is considered 20 kilohertz, where I in the input side resistance. So, putting the value for rated condition in this, so we get 1.07. This is the typical value for boundary condition. So, practically we should get less than that. In many situations people keep even 1/10. So, you can even take a typically of around 100 microsecond to ensure the discontinuous mode of conduction even for lower voltage and typically the highest power, like because at lowest voltage of input you will find this current will be corresponding to the maximum. So, there is a tendency of the converter to go into continuous conduction, but if it goes into continuous conduction then you will not get inherent power factor correction. So, we have to make sure by taking enough low inductance that in any extreme operating condition your this converter is not going into the continuous conduction, so that your inherent power factor correction condition is satisfied. Like coming to selection of the DC link capacitor. So, considering the condition of maximum ripple at the minimum output voltage, the design of DC link capacitor is made CD equal to ID upon 2 omega delta VD. So, putting the value it comes like typically all power value and twice of the you can call it the twice of supply frequency, which is second harmonics on the DC link, and 2% of the voltage ripple across the voltage of 240 volt. So, we select normally little higher value on this to make sure that this ripple is always less than typically of 2%. So, it comes 1 millifarad. And coming to the typical design of EMI filter of the input. So, design of the filter for capacitor is calculated from the same relation which we have used earlier. So, here theta is the angle between your supply voltage or supply current, and the value of here the Vm and Im are the peak value of supply voltage and current. So, putting the value, we are getting typically a 574.3 nanofarad. We select little lower value of this. So, the selected value here is 320 nanofarad. Now, coming to the design of EMI filter inductor. So, while designing the inductor for this LC filter, the source inductor is taken into consideration. So, higher harmonics in the input side by switching frequency of switching device is eliminated by using the LC filter. Therefore, an accurate filter design is essential for power factor correction converter, and the filter inductor is calculated from typically from this relation. And here of course, this total inductor is the inductor which requires, and then the source inductance. So, getting the value total, putting the value, we get 4.73 millihenry. So, the cutoff here, the cutoff switching frequency is taken typically of 1/10 of the switching frequency. So, that you are able to eliminate even all the your higher switching frequency harmonics like. And coming to the third example, a design a single phase power factor corrected AC/DC non isolated CUC converter operating in continuous conduction mode at 20 kilohertz with the following specification, with the supply voltage of 220 volt, like a 50 hertz single phase AC supply, and DC output voltage 300 volt, and power is 1900 watt with output ripple of 2%. So, this is the typical circuit, like we have a here you can call it diode rectifier, then we have a EMI filter, and then we have a your typically a CUC converter which is operating in continuous conduction mode. Of course, we have to use here the control, we call it the current multiplier approach, that output voltage regulator, then from this we get the phase form typically at the output of diode rectifier, and then we sense this current and control this current, shape the current by giving the signal to this MOSFET of this device like. So, after designing the components for giving specification, then the model is developed, and after developing the model, these are the waveform obtained for this system under rated conditions. This supply voltage, this supply current, you can see supply current closer to sinusoidal and in phase with the supply voltage. So, that there is no reactive power as well as harmonics is there, and you can see typically here, I mean the input inductor current is also continuous, as well as you can see the output voltage is regulated, and for this supply current the TAT is obtained is of order of 3.97% like so. And now coming to numerical part of this, for this buck boost converter, this is the typical relation for non isolated buck boost converter. So, you have a typically output voltage in terms of the input voltage, that is input voltage, here is the average output of the diode rectifier, which can be calculated from the supply RMS voltage from this relation. So, it comes 198 for 220 volt RMS voltage, and therefore, the value of duty cycle can be calculated from the relation, this relation putting the value. So, here duty cycle comes D equal to 0.602, that really clearly explain that the operation of the converter is in a boost mode, because above 0.5 duty cycle this converter operates in boost mode, and average input current can be calculated from power and the input average voltage. So, putting the value of output per, that is 1900 watt divided by 198, it comes 9.6 ampere. And now coming to the design of the input inductor, because you have a 3 element input inductor, output inductor, as well as the you can call it the energy transfer capacitor and the output capacitor like. So, designing the input inductor for continuous conduction mode for a 40% current ripple, this is typically relation corresponding to the on period. You are switching on the typically in across the input inductor, you will find the voltage applied Vin, and this is the maximum current ripple corresponding to that period, and this is the switching frequency. So, we get this inductor, putting the value, we get 1.55 millihenry. Normally, we select to make the continuous conduction under all operating condition. This is calculated corresponding to rated voltage, but certainly in practice we have the voltage increasing. When there will be increase in the voltage, then certainly the current will be less and ripple current may increase. So, to take care under wide operating range, the inductor is selected little above than this calculated value, and that selected value is 2 millihenry here to ensure the continuous conduction mode of operation over a wide operating range. And now coming to the your inductor output inductor design for continuous conduction mode, with the 30% ripple current. I mean that output inductor is calculated normally during the 4 off period, that is 1 minus D for continuous conduction. So, that is output voltage into the your diode conduction period for which the energy transfer for, and this is the ripple again in the output inductor and switching frequency. So, putting the value here also we get 3.14 millihenry. To make sure that it also operate in continuous conduction mode over a wide you can call it operating range, the inductor is selected as 3.5 millihenry, little higher than what we are really getting calculated to make sure that the continuous conduction mode of operation is always there in the wide voltage varying and load variation like. So, coming to the voltage across the energy transfer capacitor C1, this is the typically the relation corresponding to off period, that is Vc1 V upon D. So, here this voltage across this from this duty cycle it comes 495 volt, and considering the 10% ripple in the design of the capacitor C1. So, putting the value that it comes 3 point typically of 9 millifarad, and the value of this intermediate typically is selected a little higher than this, that is 4 microfarad. And considering the condition of maximum ripple at the minimum output voltage, the design of the DC link capacitor is made CD equal to IDC upon 2 omega delta VDC. So, putting the value in this we get this value about 1.68 millifarad, and to make sure even during dynamics also this voltage does not go over a wide range. So, and to make sure that it is more than not 2% ripple, the value of capacitor is selected a little higher than the standard value of 2 millifarad. Now, coming to the typically of design of EMI filter, EMI LC filter. So, the diode bridge rectifier output is fed to the low pass filter tuned at 1/10 of the switching frequency to suppress the higher order harmony. Therefore, the design of this LC filter can be given here C max equal to I max Im upon Vm into omega L into tan theta, where theta is typically like you can call it angle between supply voltage and current. Normally, it is considered not to have too much reactive power, only 1 degree, and this gives the value of typically capacitor of 2.2 microfarad, and certainly we select normally this value to lower than this. So, selection here it is only 800 nanofarad. Now, coming to the design of this inductor for EMI filter of LC filter, the sourcing inductor is taken into consideration. So, higher order harmonics are introduced in the side by high switching frequency of the solid state switch is eliminated by LC filter. Therefore, accurate design of the filter is essential for PFC converter. So, filter design is inductor is calculated from this relation, and where the this inductor is a sum of, you can call it like a source inductance plus the required inductance. So, putting the value we are able to get required inductance here 3.86 Henry, and the cutoff frequency is taken 1/10 of your switching frequency. So, now coming to the example 4, design a single phase part factor corrected ACD DC non isolated converter operating in discontinuous conduction mode and operating at 50 kilohertz specification, and where the supply voltage variation is 160 to 70 at 50 hertz single phase supply. Output voltage is varying 200 to 260 volt, adjustable with the nominal of 220 volt. Power output is 850 watt with the output voltage ripple of less than 2%. So, it is well, you can have a large number of solution here, that you have 3 element, all 3 can operate in discontinuous mode. Of course, this is the diode bridge rectifier followed by LC filter, and you can have all 3 so, you will get 2 to power 3 design, out of 8 design will be for all 3 CCM which we considered in previous problem. Now, you can have even 7 design, so you can take even all in discontinuous conduction mode, and after designing properly, like this converter and putting the design value here, we are able to get typically the waveform, that supply voltage, supply current, which are in phase with the you can call it like in phase, as well as the current is quite close to sinusoidal, as well as there is no reactive power burden on the supply, but you can see clearly here the input inductor current is also discontinuous, output inductor current is also discontinuous, and there is the output voltage like. So, coming to numerical part of it, the output voltage of buck converter is because it is a buck boost converter, this is the relation between input average voltage after diode rectifier and the output DC, and designing this inductor in discontinuous mode, the only difference, this is for on period. So, applied voltage V in D and the ripple current is made 0 to 2 in, means it is going to be from 0 to 2 of input peak current. So, then you can call it like typically ripple is very high. I mean, this is for boundary condition. After calculating, we have to select the lower than that, like. So, once we put the value here corresponding to this your inductor, so it comes 161 micro Henry, and we have to select certainly corresponding to n minimum supply voltage. So, we have to calculate, because supply voltage is here varying. So, we have to calculate for here, this is corresponding to the maximum voltage of 260 volt and this is for minimum of 200 volt. So, it comes 141.3 micro Henry. So, in the above expression, a higher switching frequency is considered of 20 kilohertz, where the Rin give an input resistance as per the required power, and you can call it the minimum voltage is 160 volt. Therefore, the critical value is selected for lower value than I, this is of 200 volt, and the inductor is selected certainly much lesser than any one of the two value. So, it is selected typically you can call it 100 micro Henry for to ensure the DCM discontinuous mode of operation over a wide voltage range as well as wide varying load range. Now, coming to output inductor, that also supposed to be designed for typically for discontinuous mode. So, that is calculated for maximum output voltage. So, this is the typical relation. So, if we calculate corresponding to output maximum voltage, it comes 185 micro Henry, and we calculate the minimum voltage which is normally required in application to control the voltage, it comes 124.9 micro Henry. Now, we have to make sure that it operates in discontinuous conduction mode in all these operating conditions. So, we have to make sure that it is less than even this value. So, therefore, value of the inductor is selected lower than the lowest of these two, and the inductor is selected as 80 micro Henry to ensure this discontinuous mode of operation of this output inductor. Now, coming to the typically the critical value of the intermediate capacitor, here also we are permitting now ripple twice of the average voltage of across the capacitor for boundary condition. So, keeping the value here, it comes 25.12 nanofarad, and to make this is corresponding to one voltage of typically of the supply voltage, and this is for another supply voltage of 260, this is for 200, and it comes like a 20.63 micro Henry. So, we select out of even lowest out of these two. So, we select in place of even lower than that around 15 nanofarad to make a DCM operation of under over wide operating range. And now, coming to the considering the condition of maximum ripple voltage for minimum output voltage of DC link, that is corresponding to with this relation corresponding to lower voltage of typically of corresponding to both. So, it comes 1 millifarad, and if we select for minimum voltage of 200 output volt from this relation, it comes 1.7 millifarad. And certainly, we have to make sure that the ripple is not exceeding more than 2% under worst condition. So, we select the value even little higher than the highest out of 2. So, we select around the value of DC link capacitor around 2 millifarad. Now, coming to the design of EMI filter, the Railroad Bridge rectifier fed low pass filter tuned for 1/10 of the switching frequency to suppress the higher order harmony. So, therefore, design of LC filter can be get here. So, typically your capacitor maximum value is calculated from your Im upon Vm into omega L into tan theta, where theta is taken only not to have a much reactive power burden only 1 degree here, and the value comes 1976.26 nanofarad. This is the highest value. Normally, we will select the lower than that. So, where Vm, Im are the peak supply voltage and current, and the filter capacitor is selected lesser than this, means 470 nanofarad is standard value. And for filter design, the source inductance is estimated from here, and the total filter inductor is the source inductance plus required inductance. So, from relation we can find out typically the required inductance for EMI filter. So, it comes 4.44 millihenry, and the cutoff frequency is taken as a 1/10 of the switching frequency like. So, coming to typically as a fifth example, design a single phase power factor corrected AC/DC non isolated single ended primary inductance converter operating in discontinuous conduction mode at 50 kilohertz, and following the specification of supply voltage of 220 volt RMS with 50 hertz single phase supply, and output voltage is 220 volt, and your rated power is 850 watt. with the output voltage ripple of less than 2%. So, this is a typical circuit. So, after diode rectifier we have a EMI filter, then we have a shape converter with the output capacitor. So, these are the two inductor and the capacitor and here we design this input inductor typically in discontinuous mode. So, you can just see here after designing this converter and making a model and simulating the waveform, these are the typical waveform, that supply voltage, and this is typically the supply current which is in phase with the supply voltage and almost quite clean. So, you do not have a much no reactive power button, and you do not have much higher order harmonic, and this is the input inductor current which is designed in discontinuous mode. This is the output voltage, and of course, of this current harmonic spectrum you can clearly see of this waveform of supply current, it comes 3.96, which is much lesser than 5% like or so. Now, coming to numerical part of the design of this is the relation. Again, this epic converter is also a buck boost converter. So, that is the average output voltage of diode rectifier, and this is the output voltage of the converter across the output capacitor. So, putting the value here, average input voltage from the diode rectifier is in terms of RMS voltage, it comes 198 volt, and putting the value for corresponding to output voltage of 220 volt with this average volt 1. So, duty cycle comes 0.526. It means it is sure that it operating in boost mode, because this duty cycle is above 0.5, and then we can find out the input average current from power and input average voltage. So, it comes 4.3 ampere, and from the for DCM we can find out this inductance, equivalent induction for this converter, it comes 0.127 millihenry, and then we can find out from this input inductor for discontinuous conduction mode, it comes 0.242 millihenry, and we select, because it is a DCM. So, we have to select lower than this value to make sure that under all operating condition this current remain discontinuous in this inductor. So, we select lower than that is 0.15 millihenry, and then from the equivalent inductance which we have calculated earlier and putting the value in this the input inductor, we can find out the output inductor. So, output inductor comes 0.83 millihenry, and now we select to make sure that this also operate all the time in discontinuous current mode. So, we select lower than this, it should be lower than this value to make sure you selected higher than this to make in continuous conduction mode. Of course, you can select only one component to make a discontinuous mode of operation, and considering the 20% voltage ripple at across the intermediate capacitor. So, we get the value of this C1 which get 0.3 micro, and we select little higher corresponding to make sure that this ripple is less than 20% in all operating conditions. So, it comes 0.44 microfarad. Now, coming to the output capacitor, considering the condition for maximum ripple in the design of DC link capacitor, this is CD ID equal to IDC load current divided by twice of supply frequency and voltage ripple, which is 2% of output voltage. So, it comes 1.4 millifarad, and the maximum voltage ripple across CDC is considered 2% of the VDC. So, value of DC link capacitor is selected higher than this to make sure that the ripple is not going in any case more than 2%. So, it is selected 1.8 millifarad. So, coming to the design of this LC input EMI filter, from the value of this capacitor relation in terms of IM, VM, which are the supply voltage peak and current peak, and theta is the angle between supply voltage and current, and omega L is typically the frequency of supply. So, we get this 976.3 nanofarad, and we select certainly lower than that. So, here it is selected 150 nanofarad. So, remaining we get compensation from of course, the inductor. So, it is a supply inductance, and the total inductance required is the supply inductance plus the additional required inductor which we calculate here, and from this we get this required inductance of order of 3.13 millihenry, and to make sure that it is always eliminate all the higher order harmonic. So, we select little higher than that, it is a 3.3 millihenry, and the cutoff frequency FC is taken 1/10 of the switching frequency. Now, coming to the sixth example, design a single phase perfectly corrected AC/DC non isolated canonical switching converter operating in discontinuous current mode, also known as voltage with the voltage follower control approach, operating at 20 kilohertz with the following specification with the supply voltage of 220 volt 50 hertz and single phase AC supply, and output is 220 volt, power is 950 watt with the output voltage of 2%. So, this is typically you can call it after diode rectifier EMI filter, and this is your canonical switching converter for this inductor design in DCM also. After designing the value, and model is made, and from the model the waveform are simulated. So, this supply voltage, supply current, which is supply current is in phase with the voltage, and supply current is quite clean, and THD is also much lesser than 5%, and this inductor is designed in DCM. So, that is the only component here which have to operate in DCM for discontinuous mode of operation, and this is the output voltage, which is well regulated voltage, of course, with the ripple which is of 2% in that. Now, coming to numerical part of this problem, the output voltage of the canonical switching converter is calculated from this buck boost relation, because this is also another category of buck boost converter, and this is the average voltage of after diode rectifier, that is corresponding to DC, and this is the your DC voltage across the capacitor. So, I mean, putting the value RMS voltage of the supply voltage, we can have average input voltage at the output of diode rectifier, that comes 198 volt, and therefore, we can find out nominal duty ratio from this relation. So, putting the value, we get 0.526. It means the converter is operating in boost mode, because this duty cycle is above 0.5, and the input average current is from rated power divided by average input voltage, and putting the value, we get it 4.8 ampere, and we can calculate this inductor in for critical conduction mode, because that is the specified value we can find out. So, this where the ripple is in this is twice the current flowing through this, and this comes 0.54 millihenry, and we have to make sure that we select the much lower than this. So, that in under all operating condition, even much lower than supply voltage, lower than this nominal voltage, it still remain in discontinuous mode. So, inductor is selected typically order of even around 1/4 order of that is a 0.15 micro millihenry, to make sure that it operates always in discontinuous conduction mode like. So, now coming to a intermediate capacitor designed for permitted ripple of 10% across it, and the voltage across it comes like V in and V out, that is typically the voltage across this. So, from this relation we can find out for given ripple voltage, we get this at around 2.72 microfarad, and we select little higher than that. So, that ripple is lesser than 10% of across it like. So, now coming to the considering the maximum ripple at the minimum voltage, the design of DC link capacitor is calculated of output here, which depends on load current, voltage ripple across it, and twice the supply frequency, because second harmonics is there across that, for which we are designing here. So, putting the value, we get 1.56 millifarad, and the maximum ripple voltage across CDC is considered 2%. So, value is selected a little higher than that. So, that is selected 1.8 millifarad. Now, coming to the EMI filter design. So, diode bridge rectifier output is fed to low pass filter tuned at 1/10 of the switching frequency to suppress higher order harmonics. So, therefore, design of this LC filter can be calculated from the C max equal to IM, that is the peak of input supply current, this is the peak of VM input supply voltage and the supply frequency, and the angle is taken only 1 degree, not to have any reactive power burden on the supply side. So, after putting the value, we get this 1.1 microfarad, and we normally select this value much lower than to make sure this angle is further lower. So, typically the value of this filter capacitor is selected 650 nanofarad. Now, while designing the inductor for this LC filter, the source inductor is taken into consideration. So, higher order harmonics introduced by high switching frequency of the switching device is eliminated by using LC filter. Therefore, an accurate filter design is essential for perfect correction converter, and filter inductor design is calculated from typically from this relation, where this LS is the source inductance calculated from this relation. So, from this is the required inductor. So, that comes 4.88 millihenry, and we are not very sure how much the source inductance. So, to make sure that we select normally little higher than that, where the your typically here your FC is the your switching 1/10 of the switching frequency we select here in this relation. Now, coming to an example 7, the design a single phase power factor corrected AC/DC non isolated LEO converter operating in discontinuous conduction mode, and operating at 20 kilohertz with the following specification of supply voltage of 220 volt 50 hertz single phase AC supply, and DC output voltage of 300 volt, and power is rated is 250 watt, and with the output voltage ripple 2%. So, this is typically the circuit of LEO converter. So, we have a after diode rectifier, we have a EMI filter followed by this LEO converter, and then we have a typically here output capacitor like, and this is the typical value calculated here, that VDC equal to V in into D upon. So, this is also buck boost converter. So, putting the value RMS value, we can get average input at the diode rectifier output. It comes like a 198 volt, and putting the value in the relation of this, we get output voltage 300 volt, input voltage 198, we get the duty cycle equal to 0.602, and since it is above 0.5, so we are sure that it is operating in boost mode, and from this we can find out the average input current from power and input average voltage. So, it comes 250 divided by 198, so it comes 1.262 ampere. Now, coming to the design of the inductor for discontinuous mode. So, we calculate for critical conduction from this relation, where we allow the ripple of twice of the typically you can call it inductor current, average current. So, it comes 2.36, and to make sure that it remains operates under all operating condition into DCM. So, we select 1/10 of this. So, it is selected typically of 0.25 millihenry to ensure DCM for over a wide operating range. An intermediate capacitor is designed for permitted ripple of 50% of the this capacitor voltage, and the capacitor voltage is certainly comes V in into V out. It comes like for given specification of over 98 volt, and this capacitor, putting the value in this case, it comes like 83.61 nanofarad, and we select 100 nanofarad to make sure that ripple is much lesser than typically of 50% like. So, now coming to the considering the condition for maximum ripple at the minimum output voltage, the design of DC link capacitor is made for CD equal to IDC upon 2 omega into delta VDC. So, putting the value, we get this as a 221.16 microfarad, and the maximum ripple voltage across CDC is considered 2%. So, we select the value of this DC link capacitor little higher than this value. So, it comes 250 microfarad. Now, coming to typically the output inductor, considering the 20% ripple, the expression for output inductor is calculated from this relation. Putting the value, we get 4.7 millihenry. To make sure that it operates always with the continuous conduction less than 20% capacity, we select this inductor little higher than this value. So, we select 5 millihenry. Now, coming to the EMI filter design. So, diode rectifier output is fed to the low pass tune filter at tuned at 1/10 of switching frequency, and therefore, filter design can be there, the capacitor value corresponding to the peak of supply current, peak of supply voltage, and then supply frequency, and angle, a small angle between supply voltage and supply current order of 1 degree to make calculation. So, it comes 287.13 nanofarad, and we select this capacitor value little lower than this. So, we select 220 nanofarad is selected here. Now, coming to the inductor design of this EMI filter. So, while designing the inductor for LC filter, the source inductor is taken into consideration. So, higher order harmonics introduced in the input side by high switching frequency of the solid state switch eliminated by LC filter. Therefore, accurate filter design is essential for this power factor correction converter, and the filter inductor design is typically for source inductance with the relation. So, this is the required one, this is the total one. So, we after putting the value, we get the required inductor. After putting all the values, we get 10 millihenry, and we select therefore this 10 millihenry, and cutoff frequency had taken 1/10 of the switching frequency. Now, coming to 8th example, the design is single phase power factor corrected AC/DC non isolated Shepherd-Taylor converter. This is also buck boost converter, and input output inductor operating in DCM, discontinuous mode, and at 20 kilohertz with the following specification of input supply voltage of 220 volt, 50 hertz, and single phase AC applied DC output voltage 300 volt, and power is of 1900 watt with the output ripple of less than 5%. So, this is the circuit after rectifier your say typically of your what we call it the Shepherd-Taylor converter. So, after designing in typically in DCM, we and making the model with these value, putting the value that we get the simulated waveform supply voltage, and this is the supply current you can see in phase with the supply voltage and almost close to sinusoidal, and this inductor current, input inductor current which is discontinuous, and this is the output voltage. And after harmonic spectrum, you can see this input current, supply current, which have a TAD only of 3.59% like. And coming to numerical part of solution of this problem, so output voltage of Shepherd-Taylor is calculated from this buck boost relation, and of course, the average input is after diode rectifier is calculated from RMS voltage, so it comes 198 volt, and putting the value in this relation input output voltage and input voltage, we get the duty cycle 0.602, and this makes us to conclude that it is operating in boost mode, because this is above 0.5, and we can calculate average input current from power divided by average input voltage, and it comes 9.6 ampere. So, coming to the design of the input inductor for discontinuous current mode, this L just for critical value for corresponding to twice of the ripple. So, it comes 0.31 microhenry, and the input inductor is selected typically much lesser than, to make sure that it operates under all operating condition discontinuous mode. So, it is taken is 0.1 millihenry for operating in discontinuous mode like. So, coming to intermediate design of intermediate capacitor to permit the voltage ripple around 45%. So, voltage across it comes V in upon V output. This is average input voltage, this is output voltage. So, it comes 498 volt, and this capacitor is calculated from this relation for a given ripple of 45%. Here the value is put, and we get this as a 0.85 microfarad. We select the value little higher to make sure that voltage ripple is always less than that. So, it comes, the capacitor is selected 1 microfarad. So, coming to design of output inductor in DCM, and this is the again for the boundary condition that the ripple is twice of the output current or current of the flowing through the inductor, because this current in the inductor is same as the output inductor, because through this energy it is transferred, and putting the value in all this relation. So, we get the value of 0.472 millihenry, and to make sure that this operates in discontinuous mode, we select 1/3 value of this. So, it comes 0.16 millihenry operating in DCM. And coming to typically for selection of output capacitor for a given voltage ripple of typically of 5%. So, considering the maximum ripple at the minimum output voltage, the design of capacitor is made. C output equal to IDC upon 2 ohm delta V 0. So, we put here it comes like a 0.67 millifarad, and the maximum ripple voltage across considered as a 5%, and value of DC capacitor is considered as a 1 millifarad. And that now coming to design of EMI filter. So, diode bridge rectifier is fed to a low pass filter, which is tuned to 1/10 of the switching frequency, and the inductor design capacitor for this LC filter is calculated from this relation Im upon Vm into omega L into tan theta, taking a theta around 1 degree and putting the value of input output voltage and typically value. So, we get 2.18 microfarad. We select much lower than that because this is the maximum value. So, we select typically this capacitor is of 780 nanofarad. Now, coming to design of filter inductor of this MI filter, this is the source inductance relation, and the required inductor is source inductance plus required. So, this is the relation. So, we get from this required inductor, putting the value here 5.66 millihenry. This is the minimum inductance. So, to make sure we do not know the supply inductance, so we take little higher than this. So, we select here you are around typically 6 millihenry. Now, coming to the typically the numerical example with the 9th numerical example, design a 300 watt power factor bridgeless zeta converter operating in continuous conduction mode to maintain the DC link voltage of 300 volt with a percentage ripple of 1% and permitted ripple in the input and output side inductor and intermediate capacitor is 20%. The power factor correction converter is operated at 220 volt, 50 hertz input, and while switching frequency is 40 kilohertz, and calculate the value of input and output inductor, intermediate capacitor and DC link capacitor. So, these are typically of bridgeless zeta converter circuit. So, we have of course, these two inductors are identical, capacitors are also identical, inductors are identical because they are operating in positive negative half cycle, but diode bridge is eliminated. And coming to the with this circuit for the numerical relation, this is the average voltage, typically in terms of the RMS supply voltage 198 for given 220 volt, and from the input output relation we get the duty cycle for output voltage of 300 volt and input average voltage of 198, it comes 0.6024. It makes sure for buck boost converter, this converter operating in boost mode because this duty cycle is above 0.5. Now, coming to the typically the value of the average input inductor input current, from power divided by the input power, total power divided by the input voltage, average voltage, it comes 1.15 ampere. And now we can calculate the input inductor operating in CCM, and both inductor of input we take in typically in identical because both are operating in positive and negative half cycle. So, considering 20% current ripple of these inductor and putting the value for 20% current ripple for on period. I mean this is the voltage applied and D is corresponding to your duty cycle, and F is the switching frequency. We get this value 9.841 millihenry. Therefore, these two input inductors are selected as 10 millihenry to make sure that this converter is always operating in, inductors are operating always in continuous conduction mode. Now, coming to output inductor operating in continuous conduction mode, again we selected 20% current ripple, and the minimum output inductance calculated from this relation of output voltage for a given current ripple, and it comes putting the value here of your output voltage and switching frequency and ripple current of 20%, and duty cycle we get this as a 14.9 millihenry, and we select a little higher than that. So, we select this as a 15 millihenry. Now, coming to design of intermediate capacitor. So, we consider 20% ripple across them, and this is the relation for this intermediate capacitor, and putting the value corresponding to the equivalent to a load resistance, and then the output voltage, duty cycle and switching frequency and ripple voltage across this capacitor. So, it comes 151.2 nanofarad, and we select to make them continuous voltage across C1, C2, we select this is higher than this. So, we select 250 nanofarad to ensure continuous conduction of voltage across these capacitors. Now, coming to the output capacitor DC link capacitor design from CD equal to ID upon 2 omega delta VDC, and calculating this output current and putting the value here. So, it comes 530.78 microfarad. So, DC link capacitor is selected higher than this as a standard value, typically of 660 microfarad. Now, coming to the 10th numerical example, design a 500 watt power factor corrected bridgeless Cuck converter operating in discontinuous conduction mode for output inductor only to maintain the DC link voltage of 300 volt with the percentage ripple of 4%. The percentage ripple in the input inductor and intermediate capacitor is 20%. The power factor converter is operating at with the input voltage of 220 volt 50 hertz and switching frequency of 40 kilohertz. Calculate the value of input output inductor, intermediate capacitor and the output DC link capacitor virtually. So, this is the circuit for bridgeless Cuck converter, where one for 1/2 cycle upper Cuck converter operate, for negative half cycle the lower Cuck converter operate, and these typically the component of input inductor, the energy transfer capacitor and output inductor, they are identical. Like to make sure that positive and negative half cycle of the operation is identical. So, now coming to typically the numerical part of this, average input voltage appearing across the input of the converter, or you can call it at the output of diode rectifier will be V in equal to, that is calculated from RMS supply voltage, average voltage. So, it comes 198 after putting the value into it, and now the duty ratio is calculated from a given output voltage for a given input voltage, and this comes again 0.6024. It makes sure that this is operating in boost mode, because if duty cycle is above 0.5, it means it is operating in boost mode. Now, coming to calculation of component. So, we calculate the input average current from the power divided by input average voltage. So, it comes to putting the value of this of power and your input average voltage, it comes 2.525 ampere, and the input inductor we say that they are operating with the 20% in continuous conduction mode with the 20% ripple, and the value of the capacitor both from input applied voltage for on period and switching frequency, and putting the value of all these variables. So, it comes 5.904 millihenry. To make sure that it operates all the continuous conduction mode, we select a little higher than that value. So, therefore, the L1, Li1 and Li2 are selected as 6 millihenry to ensure continuous conduction mode of operation. And now, coming to output inductor operating in discontinuous mode. So, relation is for corresponding to output 1, and here we say for boundary condition the ripple is twice of the current flowing through this, that is the current through this output inductor is the same as the load current. So, the average of this will be double of P will be double of this for just boundary condition, and we calculate this, it comes 894.6 microhenry after putting the value of all these variables. And however, we have to select this value lower than that to make sure that your these inductors are operating all the time discontinuous mode, because that decides the type of control we are using, like as a voltage follower approach. So, hence LO, both the inductors are selected as 2/3 of this value, that is 596.4 microhenry. Now, coming to the designing of intermediate capacitors for both the let us say a converter of positive half cycle, negative half cycle. So, we are considering 20% voltage ripple, and the C1, C2 are calculated from this relation for a given voltage ripple across it. So, the voltage across this capacitor is also sum of input output voltage, of which the ripple is there. So, putting all the value, we get 252 nanofarad. To make sure the capacitor have all the time continuous voltage across them, so we select a little higher than that value, and we select this as a 350 nanofarad to ensure continuous conduction mode of the voltage across these capacitors. Like now, coming to the design of DC link capacitor, the relation with CD equal to ID upon 2 omega delta ID, that is the load current, that is the load voltage ripple, and 2 omega, because it does not depend on switching frequency, depends on supply frequency because of second harmonics here. And after putting all these value here, we get this as a typically 221.16 microfarad. To make sure this ripple is always less than the 4% ripple which is specified here, we select this capacitor higher than this value, and the DC link capacitor is selected as 440 microfarad. Now, coming to the 11th example, design a 300 watt bridgeless single ended primary inductance power factor converter operating in discontinuous mode only output inductor to maintain DC link voltage of 300 volt with the percentage ripple of 4%. The permitted ripple in the input side inductor and intermediate capacitor is given 20%, and power factor correction converter is to be operated with the input of 220 volt 50 hertz and switching frequency is 40 kilohertz. Calculate the value of input and output inductors, intermediate capacitor and DC link capacitor. So, this is the power factor bridgeless single ended primary conductance converter, and here also both the inductors of input are identical, capacitors of energy transfer is also identical, and the output inductors are identical. That is different, these inductors are designed for DCM, so that you can apply inherent power factor correction only with the voltage follower approach by controlling the output voltage. Now, coming with this as a numerical solution, so average input voltage appearing across the input of the converter comes V in to root 2 upon Vs upon pi, that is the RMS supply voltage. So, it comes 198 after putting value of Vs of 220 volt, and now the duty cycle for a given input output voltage. So, we have output voltage 198 and input is 300 volt. So, we get the duty cycle, it comes 0.624, and we are sure that it is operating in boost mode because the duty cycle is above 0.5, which certainly concludes that the converter is operating in boost mode. Now, coming to the calculation of input current, average input current, that is from power divided by input average voltage. So, 300 upon 198 and it comes 1.515 ampere, and the input inductors are operating continuous conduction mode. So, for the 20% current ripple in the input inductor, we can calculate the input inductors from this relation corresponding to on period, for this deriving this relation. So, it comes 9.841 millihenry to therefore, the L1 these two inductors are selected as 10 millihenry to ensure the continuous conduction mode of these inductors over a wide operating range either of input voltage or the load. Now, coming to the output calculating the output inductor for discontinuous mode, we calculate this calculation of this from output relation for boundary condition, and boundary condition because inductor current, this inductor currents are the same as the output inductor output load current, because both were average is same. So, we put twice of this because we start from going to be twice of 0 to twice of value for boundary condition, and putting the value for this, it comes after putting all these value, we get 1.949 millihenry, and to make sure this is always operating discontinuous, we select this LO to 2/3 value of this. So, we select around typically 995 microhenry to ensure that it is operating always in discontinuous mode that corresponding to minimum input voltage, which will cause the maximum current in this inductor. Now, coming to design of intermediate capacitor, so considering 20% voltage ripple in the intermediate capacitor, the design of this comes C1, C2, and the voltage across this capacitor is sum of input output voltage. So, putting all the value here, it comes 151.2 nanofarad. So, to make sure that ripple is always less than, so we select this. Therefore, C1, C2 are selected as 250 nanofarad higher than this value to ensure continuous conduction mode. And then the DC link capacitor designed for output capacitor, CD equal to ID upon 2 omega delta VD, and putting the all this value typically for power and output voltage, and with voltage ripple of 4% of output voltage and corresponding to second harmonics in the output voltage. So, it comes 132.7 microfarad, and this DC link capacitor is selected a little higher than this to make sure the voltage ripple is never go more than 4%. So, it is a 220 microfarad is selected for this DC link capacitor. Now, coming to the 12th example, the design of 200 watt power factor corrected bridgeless flyback converter operating in discontinuous mode to maintain the DC link voltage of 50 volt with the percentage ripple of 4% in DC link capacitor. The power factor converter is operating with the input supply of 220 volt 50 hertz with the switching frequency of 45 kilohertz as a turns ratio of 2 to 1, and calculate the typically calculate the transformer inductance and DC link capacitor for this converter. So, this is bridgeless flyback converter. You can see the diode bridge is completely eliminated. So, we have to calculate even the typical values of output capacitor as well as the magnetizing inductance for operating that this converter in discontinuous mode. So, virtually magnetizing inductance, this is designed for discontinuous mode. So, coming to the solution part of the input voltage appearing across the converter is input is equal to √2 into Vs upon pi, and putting the value here it comes 198, and from this relation because N2 upon N1 is given. So, we can calculate the value of duty cycle, it comes 0.3355. Well, now coming to the design of magnetizing inductance in DCM. So, we calculate this as a corresponding to boundary condition, because here we are permitting corresponding to typically the ripple of twice of the current through it. So, putting the all value it comes 45.66 microhenry, and to make sure that it is always operating in discontinuous mode. So, we select the value of inductor in DCM as a 30 microhenry, which lower than this or so. And now coming to design of output in the capacitor, that is ID upon load current divided by second harmonics of supply frequency 2 omega into delta VDC, that is the output voltage ripple, and putting the value of all them with the 40% ripple it comes 3.1847 millifarad, and we select this higher value to make sure that ripple never goes more than 4%. So, DC link capacitor is selected 3.3 millifarad. Now, coming to 13th example, the design a 300 watt power factor corrected bridgeless isolated cup converter operating in discontinuous mode to maintain the DC link voltage of 100 volt with the percentage ripple of 4%, the permitted ripple in the input inductor and intermediate capacitor is 20%. Power factor corrected the power factor corrected converter is operating at with the supply of 220 volt 50 hertz with the input and the switching frequency taken as 45 kilohertz. The tensor ratio is given 2 to 1. Calculate the value of input and output inductor, intermediate capacitor and DC link capacitor. So, this is typically a bridgeless cup converter. You can clearly see here we have a even in a bridgeless. So, here the input inductor output inductor is shared together, but of course, all components are shared with the capacitor energy transfer capacitor and then the transformer. So, you can have for DCM we can have 2 to power 3 design with one continuous and remaining discontinuous. So, we can design even only one element as a discontinuous in this converter, and that can also give the same performance as inherent power factor correction with voltage follower approach. Now, coming to the numerical part of the design. So, we say that we in average input voltage here applied to the converter is 2 √2 upon Vs upon pi, where Vs is the RMS volt supply voltage. So, it comes putting the value of Vs it comes 198 volt, and now the duty ratio is calculated from this relation. This is a relation for buck boost converter, but along with that we have a turns ratio. So, putting the all the value we get here duty cycle 0.5025. So, it is just operating very close to the 0.5 duty cycle, and transformer is responsible to transfer this. You can call it the input voltage to output voltage with the isolation, and the average input current from power and input average voltage we can calculate, it comes 1.515 ampere, and design input inductor in DCM for a 20% current ripple. So, we can find out input inductor which is shared for on during for on period with the given ripple of 20%, and it comes 7.297 millifarad, and we normally select a little higher than that to make sure that ripple is never going more than 20%. So, therefore, the L1 is selected as 7.5 millihenry to ensure DCM over a wide operating range. And the coming to design output inductor design in DCM, so that converter operate in DCM. So, we calculate this output inductor corresponding to for on off period with the ripple of twice the output for critical value. This is the critical value for critical conduction. So, that is the numerical value we can calculate, but after putting all these values we get this 184.26 microhenry. This is for DCM boundary condition, but we have to make sure for DCM it is selected lower than this value to ensure the converter is always operating in discontinuous, hence the L0 is selected less than LOC calculated value and it is selected as 150 microhenry. And coming to design of intermediate capacitor, again for continuous conduction mode, voltage across these capacitors. So, it comes 20% of voltage ripple across both the capacitors. So, we can calculate C1 from this relation, that is on input side of the transformer, and putting corresponding to the turns ratio here, it is calculated, it comes 422.95, and the output capacitor which is calculated from output side, and putting the all value, it comes 1.675 microfarad. Hence, the C1, C2 are selected higher than these value to make sure that voltage ripple is always less than the specified given value in design as a 20%. So, we are selecting them as 500 nanofarad, which is higher than a calculated value, and 1.8 microfarad, which is also more than your calculated value, to typically to make sure that these two capacitors are always having voltage across them continuous. And coming to the your output capacitor design, CD equal to ID upon 2 omega delta VDC. So, putting the value ID P upon V0 and all this value, we get 1.194, and to make sure that this output voltage ripple is less than 4% in all operating conditions, we select this value higher than that. So, DC link capacitor is selected as 1.6 millifarad. Now, coming to the 14th example, design a 50 watt 500 watt power factor corrected bridgeless isolated single ended primary inductance converter operating in discontinuous mode to maintain the DC link voltage of 200 volt with the percentage ripple of 4%. The permitted ripple in the input side inductor and intermediate capacitor is given 20%, and power factor correction converter is operated with the supply of 220 volt 50 hertz, and the switching frequency is of 45 kilohertz, and the turns ratio is selected typically 2 to 1. Calculate the value of input output inductor, intermediate capacitor, and the DC link capacitor. Now, coming to the numerical part of it, the average input voltage is calculated from this relation of diode rectifier output relation. So, putting the value of supply RMS voltage in, and it is coming as a 198 volt, and now from the relation from the output voltage from the turns ratio and then buck boost relation, converter relation, the duty cycle comes typically D equal to 0.67, and the converter in this case is operating in the boost mode because this duty cycle is above 0.5. Now, coming to the value of input average inductor current from the power and average voltage, it comes like putting the value 2.53 ampere, and the design of input inductor in DCM considering for the 20% current ripple in the input inductor. So, design is given here from the on period, and putting the value of this, it comes 5.83 millihenry. Therefore, L1 is selected 6 millihenry to ensure all the time continuous conduction mode, and the design of high frequency transformer operating in discontinuous mode. So, it is a boundary condition we can calculate because that is a definite value for where the output inductor having the same current as the your load current. So, we take load current twice of load current of average load current as a ripple for boundary condition, and keeping the all the values here, we get 586.67 microhenry. To ensure under all the operating condition, we select this much lower than that, typically less than 1/3. So, LM is selected less than typically LMC, and it is a 150 microhenry. Now, designing the intermediate capacitor in CCM considering 20% voltage ripple across the capacitor. So, design of capacitor is calculated typically from this relation, and here typically the voltage across the capacitor is like your input output addition and with the turns ratio. So, it comes 467.62 nanofarad to ensure the in CCM. So, we select the C1 selected higher than this value, that is selected as 15 nanofarad to ensure continuous conduction of voltage across this capacitor. And now, coming to design of this DC link capacitor of output. So, CD equal to ID upon 2 omega delta VD, and keeping the value all value, it comes putting this. So, it comes 497.61 microfarad, and we select this higher than that. So, DC link capacitor selected is 660 microfarad to ensure that voltage ripple never go more than 4% under wide operating conditions of the converter. With this, we would like to summarize this. So, in the summary, the buck boost converters improved power quality converters demonstrate excellent performance characteristic over a wide range of supply voltage for improved power quality with the power factor correction as well as no reactive power burden, and the power factor power circuit diagrams and operational principle of several type of buck boost derive improved power quality converter like Kux, Epic, Zeta, Leo and canonical switching converter are presented, and the bridgeless configuration of these improved power quality offers the low conduction losses as well as phi devices count. Based on this, various bridgeless buck boost converter are also demonstrated. A number of practical examples of buck boost derived improved power quality converters are given with a view of proper design exposure while considering the improved power quality performance at the grid like. And these are the references which we have taken into in all this work, and then thank you.